Heidi, can I get a sound check? Or Marco? Can you hear me, Eddie? Hey guys,
Oh,
can you
yeah.
hear me?
Yeah, I can hear you.
Okay,
I can hear
awesome. Nice. Man, I just found out one of my colleagues is the son of a Nobel Prize winner. I was looking at his website. It's like, can you imagine being the son of a Nobel Prize winner? It's like, what would the dinner conversation be like? Wow. Oof. This explains something. Okay, guys. Um, so first of all, I'm sorry. I miss classes every once in a while, but try not to miss them so many in a row or so early on in the semester. Sorry about that. I'm gonna try to like basically get us caught up. And so what I did is I recorded. There's like ended up being in 3 segments, but it's about maybe 2.5 hours of video, and that's on YouTube, and it's sort of jumping ahead from where we are. So we're going to finish this slide deck 3, go to slide deck 4, and my video recording or the record is for slide deck 5, so that you guys don't get into a time crunch. So you'll have, hopefully you'll be able to sort of catch up on that. And so that's should be on the Canvas right now. And that's basically going through model of the MOS transistor, and how do you basically a first level model of the MOS transistor from a device perspective, and calculating the IV currents, etc. Hopefully you've seen some of that stuff before, so hopefully it'll be a review, but it's something that we were going to have in slide deck 5, and so it's up now, and we're just going to go around it basically to catch up, and we'll finish 3 today and hopefully get a good start on 4. Derek, I'll try to cover the capacitance portion in person, but actually I'm not sure what I'll do with that. Good question. I was gonna do the capacitance portion, but I realized I wanted to get more in depth in the capacitance because I think it's important. So I don't know. I'll play it by ear. I'll see what happens. So, but I think I'll go into more depth either if I'll do it in person or on YouTube. So Tunji is asking about slide deck 4. I believe it's on Canvas, but I have screwed up Canvas before. Can you guys see that? Anybody can answer that? I see it, I think. Let me see, modules. Nope, I skipped slide deck 4. duh. No, Tunji. I screwed that up. Using a CMOS chips, circuit MOS switch. I screwed up. Hold on, guys. I'm going to put this slide. I'm going to put that up. Slide deck. Or slide deck. Or how did I screw that up? Just give me a second, guys. Let me take care of that. Slide deck 4. So this should be really. Module name. New contents to. Sorry, guys. So it should be up there now. Can you guys see it? No, hopefully you guys will see it by the time we're.
Yeah,
Okay.
we can see it.
Okay, great. Thanks. Sorry about that. Fail. Okay. So. All right, guys. Okay, so let's get going on slide deck 3. So I think as a review, what we were talking about is building a CMOS chip. And the idea behind building a CMOS chip, I guess the main thing to remember is that it's a sequence of steps. Sorry, one of you guys is maybe it's Justin. Thank you, Justin. So it's a sequence of steps, and it involves lithography. So you basically do step after step in the silicon. And then after you're done with that, which is most of the steps in the silicon involve implantation of different dopants, et cetera, into the silicon. But it's basically happening across the whole wafer at the same time. So you're building all the circuits on the wafer at the same time. That's an important concept. Second important concept is to do that, you are basically using a lithography process. You have to be able to mask off different parts of the wafer to build the transistors where you want it. Then all the transistors are sitting next to each other. The transistors, you can't have transistors sitting on top of other things, or on top of each other, I should say. So they all have to be sort of, it's called a planar process, meaning that all the transistors are on the surface of this wafer. And then once you get past the silicon, then you start building up layers of metallization with dielectric layers in between. And these serve as the connections between the transistors. Okay. Now those connections, these metal connections, are sort of, they're all sitting on top of each other, and you need them to connect across. So, things will come up, go across, and vice versa. You need all this stuff to route all these billions of transistors together. Okay, so basically at the end, you end up with something like this, which is, the three-dimensional perspective. Most of the time we draw stuff looking kind of this way. So, we draw stuff at, this sort of cross-sectional thing like that, where this is the length of the transistor, and this is the source and the drain. This is the poly. This is kind of looking at from this point. But we need to also remember that there is this width. So we have the length of the transistor, and then this direction is the width of the transistor. And there's interesting stuff going on there too. So if you look at it from this point of view, this polysilicon, where it's next to this source drain, makes the width of the transistor, but once it gets beyond the source drain, it's acting as an interconnection. Okay, and you have connections going to the drain and source that way. Okay, so that's the different layers. And again, to make sense of those, make this process make sense, we need these masks and the photolithography process to block off or open up different areas on the chip to do these things with. Because again, everything's happening. The equipment that's doing the implantation, the doping, the metal deposition, the oxide deposition, the oxide etch, all this stuff can't tell the difference between, there's just operating on the whole wafer at the same time. So the only way to put the patterns that you need to make transistors with this lithography steps, where you create basically masks using photoresist, using mask, using lithography. You're masking off different parts of the wafer and doing these functions. So as what you'll do if you're designing these masks is you treat each individual mask separately. So you'd have a mask for the end well, for example, and this mask would just, so let's say we're going to build this circuit. So what is this circuit? Well, it looks to me like you've got a PMOS transistor here, because it's this slightly dashed line. There's no reason you guys should know this, but just sort of take my word for it. The slightly dashed line represents a N well, so that's where a PMOS transistor wants to live in there. And this guy is outside the N well, so it's sitting in the substrate, so that's got to be an NMOS transistor. How do I know it's a transistor? Well, again, you guys don't know this, but this is, I guess, kind of the key to all this stuff, right? So these represent poly lines, polysilicon. And anytime I have a polysilicon line going across a diffusion, so these are diffusions, whenever this polysilicon line is crossing the diffusion, means that I have, remember we had this self-aligned process. So anytime I have something like this, means that I have the poly that masked off the source and the drain. And I end up, so whenever I have, again, a poly crossing this active mask. So this active mask basically sets the implantation after the polysilicon. So that was a self-aligned process to make sure my source and drains end up exactly here and here. So they line up exactly with the polysilicon gate, which coincidentally happens exactly the same time as this guy. So the polysilicon gets deposited for both the N and the P at the same time. So you'll see in the polysilicon mask, this is the gate for the N. This is the gate for the P. Anytime the polysilicon is not overlapping with the so-called active. Active is any place there's active, there is a gate oxide being deposited, it means a thin oxide. So any place there's an overlap of polysilicon with active, there's a transistor, and you can tell if it's, so here is, there's no transistor, because notice that there's this, if I put this on top of that, there is no active layer up here. So up here, there's no, this is just an interconnect. It's polysilicon acting as an interconnect. Only where there's an overlap will there be a gate. Okay, and only when there is a, when there's an N well, and there's an N well overlapping the active, is there going to be like a P MOSFET. And only when there are these contacts, this contact layer, am I going to be able to make contact to either polysilicon or to the source drains, to the N pluses. And only when I have metal one layers do I get, you know, connections to the metal. So these metal layers are making contact to the source drains. So this is the you know, the toughest part of this class to talk about, because we, unfortunately, because of the pandemic and teaching online and stuff, you guys don't have access to the lab, so we can't do any layout. But if so, it's a little difficult to understand. But anyway, just the main point I want you guys to take away from this is that these masks are our way, the designer's way of communicating to the foundry where to put what. But it's really our job, if you're doing a silicon, the chip design, of creating these masks. The people working at the foundry just take these masks or create the masks from our databases and just go through the process steps. And then in the end, that creates the chip that we want. But they're not going to worry about what you tried to build here. They're just going to make what you tell them through these masks. This is your only way of communicating with the foundry, through these masks. So the foundry already has a process. They've told you what it is, and then you make the masks based on that process. Now, this sounds like a really, how should I put it? It looks like seems like a very time, you know, it's like if you were going to draw every single transistor by hand, etc. It would be a very tedious process. But in effect, most of this stuff is going through a process. You start at the Verilog level, and you have tools, these computer-aided design tools that go from your Verilog to a synthesized netlist. So at this level, so Verilog, I don't know how many of you guys are familiar with Verilog. It sort of looks like C, but it's got hardware components. Like it understands what you may mean by things happening simultaneously, or latches or flip-flops, etc. So at this point, it looks like kind of like C-ish code. At this point, it looks like you know, schematic level stuff. Whoops. And then this goes to a place and route. So at this point, it looks like these transistors get placed. And basically the tools are expensive and they're smart in the way they go from Verilog to your place and route. So you don't have to sit there and draw transistors for the majority of the chip. Okay. So for like 99% of the chip, you can go through this process. But it ends up that this process doesn't create the absolute best, believe it or not, like the tools aren't as good as humans when it push comes to shove. And they're like doing the best they can. But when you basically have to do this hand drawing when it gets to the most high performance part of the circuit. So let's say you have stuff that's running at multi-gigahertz through your chip, like data paths and things like that. Those you end up having to do some of those by hand, or IO circuits that again are, if you've got a 40 gigabit per second Ethernet output out of your chip, that's going to be designed by hand by somebody. Okay, like this place and route tool, these things typically work, I think, in the hundreds of megahertz clock rates. They're not going to be able to take you to 2-3 gigahertz or higher clock rates. Okay, so this is, but the good thing is the majority of your chip is not running that fast. Then you have like a 2 gigahertz clock chip. Most of the chip is just not running that fast. Most of the chip, there's a few data paths that are running at that speed. And that's when you have to kind of like hand hone some of the stuff. Okay. So anyway, back to the main point is that the way you communicate with the foundry are through these masks. Okay. And the way the foundry communicates with you is through these things called design rules, okay, which are the guidelines the foundry, the manufacturing plant is telling you guys, these are what they can make. So what they tell you for the design rules is what mask does what. This is a pretty simplified way of looking at the process. In a typical sort of 65 nanometer process, which again is relatively old, you might have 50 masks or so. And all these masks sort of overlapped on each other is what creates your devices. So these complicated guidelines, the foundry is telling you in these design rules what they're going to be doing with them. And they're also telling you, if you try to build some structures, they're not going to work. They're telling you like what they can build and what they can't. Okay, so let's use an example. Let's say you're going to use, you're going to route 2 polysilicon lines. Okay, so you're going to draw 2 polysilicon lines next to each other. So put this on your mask. So if I was going to look at this from a cross section, this guy, if I was going to look at it from this edge, it would look like 2 polysilicon gates. Looking at it from this end as a cross section. So this would be the silicon. This would be polysilicon. And this would be some oxide. Okay, that's what it's going to look like. Now, they're going to tell you, do not make these 2 lines. Don't make these 2 lines. Don't draw them closer than a certain amount. So they're going to say, hey, don't draw it closer than, I don't know, 0.2 microns. Otherwise, my equipment is going to make by the time, if you make this like 0.1 micron, if you make it 0.1 micron, you think you think you're gonna get this. You're gonna get two polysilicon guides lines that are not connected. But in effect, because my equipment isn't my lithography equipment in this particular process is not good enough to resolve the space, is not good enough to mask the space or create an opening in the space, depending what it is, I might actually get a short. It might look like a continuous polyline. So it might look actually, if I try to do the same thing, so it's going to look like if I draw them too close to each other, then it's going to look like they're going to might get shorts across it. So instead of two lines running parallel to each other, you'll get one line that's sort of melted together, whatever the process is. So the foundry says, hey, like keep these lines, keep this line spacing. Don't go any lower than this line spacing. Another thing they'll tell you is, let's say if you want to draw two polysilicon lines that are too narrow. Okay. Let's say they tell you, hey, if you make something that's less than 0.1 micron, I'm just making up these numbers. Okay, you think you've drawn two really narrow polysilicon lines, but in fact, when I do my etch process or my lithography process, these will actually come out as looking at some points you might get like an opening in these lines. I can't resolve these lines. I might get God knows what. Like it won't be, you'll get an open going through. So basically the design rules are a set of things that will tell you, you can basically give you limitations of what the foundry, the manufacturing plant can build, but they're in the language of the geometric sizes that you are permissible in these different masks and the overlapping of these layers that are permissible in these masks. For example, we talked about, I talked earlier about, where you have, when you have a active layer, let's call this active, overlapped with a polysilicon, you get a transistor gate, right? So if I draw the cross section of this, looking at it from this direction, I'll end up with something that looks like, so this will be, whoops, let me just try to make it make sense. So I'll draw it like that. Maybe an offside underneath here. So basically you'll end up with a transistor. If I draw poly on top of active. Okay, but what if I draw, for whatever reason, I draw something like this. I draw my poly, let's say I want to make it really small. I don't know why I would do this, but let's say I draw my poly here. Well, if it's possible, one, they can't resolve an active piece this thin, okay? And I certainly won't be able to make a connection to something this thin because it's too narrow to put a V on. So I might end up with most likely I will end up with something like, I won't even end up with anything here, maybe at all. Okay, so basically they'll tell me, look, don't let this edge get too close to that edge. So it's a, like they'll tell you from layer to layer what kind of tolerances they have to build these devices. So I'm making a pretty exaggerated example here, but like any other manufacturing process, from layer to layer, you know, as they're going through from step to step, there's some misalignment. As accurate as this equipment is, there'll be some misalignment of these different layers. And if you don't allow enough separation or enough overlap or enough sort of slack, in whichever way you want to look at it, if you don't put enough slack in there in your geometries or whatever you're trying to do, for the manufacturer to be able to build this thing, you'll get some, basically you'll get shorts, get grounds, or more likely you'll get a higher number of defects if you really push things to the edge, right? Some chips will come back and work and some won't. Okay, so let's look at some of these rules. Okay, so I've been trying to like tell you guys about this stuff. Maybe these drawings are going to be a little bit better. So if you look at how you build an NMOS, again, it's where you have, you draw an active layer, which the active layer, basically wherever there's active, you can put in your transistor. It means there's a thin layer of oxide wherever there's active. Then you put polysilicon on top of that. When the implantation happens, whether you use an N-select mask or a P-select mask, you'll get an N plus or you get a P plus. In this case, it's a N plus because it's an N-select mask. And then you'll want to mask this to get contacts and metal lines connected. So that's what an NMOS looks like without a substrate connection. Okay. So you basically see layers like active, like poly, like N-select, like metal one, etc. Okay. And similar things with PMOS, except PMOS will have an N-well and a P-select to distinguish it from the NMOS. Another thing about both NMOS and PMOS is you'll need to make contacts to the substrate. So remember that the substrate is P. So besides the source and drain, also need a connection to the P substrate. That ends up being a P plus connection. Okay, so you need periodically to drop these substrate connections. Same with the PMOS is you'll need to put in N plus, because you have an N well. So you'll need to make an N plus connection to the substrate. Okay, and together that makes the transistor. So you have the NMOS transistor and the PMOS transistor here. This is the contact to the substrate contact to the N well. And these will be the source and drain for the NMOS, source and drain for the PMOS. Okay, so the layers, those are the transistors. The layers on top of the transistors are the metal layers. So you need to have these different layers. There's dielectric in between. But if you want to make contacts between these guys, you need to basically open up connections between this through the dielectric, and those are in the form of these things called contacts and vias. Vias, those are basically connections between the metal layer. Contact is any connection from metal one only. So this metal one to diffusion. So that's, N plus or P plus, or to polysilicon. That's called a contact. So here there's a metal 1 to polysilicon contact, and here's a metal 1 to diffusion contact. You could also put a contact to get to, say, this P plus if you wanted to. Okay, and then vias are connections between metal layers. And so a via 1 is a connection between metal 1 and metal 2. Via 2 is a connection between metal 2 and metal 3, and so on. So it can basically stack up interconnection. So again, notice that all the transistors in a process are always sitting next to each other. So if you have an NMOS, PMOS, whatever you drew, but you never have, a PMOS down here below an NMOS because everything's happening in a planar process. So the transistors are sitting in a two-dimensional space essentially, and the metallization is happening more like three-dimensionally. Each layer is two-dimensional, but the layers are sitting on top of each other, and you can make connections between the layers. Okay. No. Okay, so we talked about this. So now if you're looking at, so again, the interconnection layers, if you overlap, let's say if this was two metal 1 layers, if you overlap two metal 1 layers like this, there'll be a short because they're sitting in the same layer. Okay, but if you overlap, say this is metal 2 and this is metal 3, if you overlap them without putting in a via here, without drawing a via, then they're just routed on top of each other because there's a dielectric in between. So the nice thing about these interconnections is as you build up the number of layers, you can get really complex interconnections going because you can jump. I don't know if you guys have done any routing in printed circuit boards or whatever, but just basically you can just jump up and go across. It's kind of like having the intersections on the highway in LA where you have these raised bridges that allows you to cross across each other. Okay, again, go ahead, sorry.
Why was metal 2 and metal 3 not connected?
Yeah, so if you look at metal 2 and metal 3, again in a cross section, try to get as close to the same picture. So if this is metal 2,
I know you mentioned the via, but how can we tell from the image?
So if you actually had a via here, it would look like something like this. It would look like a via. Unfortunately, this again, if you had the computer-aided design tool, it'd be easy to show you guys because it's pretty obvious. But like from the top, it would like this is what like a contact would looks like. If I didn't have these boxes here, would mean there would be no contact there down from metal 1 to these diffusions. But those black boxes tell me there's a contact. So like these black boxes tell me there's a contact. So for example, this is metal 1. So this black box tells me there's a contact from this metal 1 to this diffusion.
Okay, thank you.
Sure. This is like, I don't know what to tell you guys. This is like I'm just kind of trying to do it like you really need the computer-aided design tools. I know this is like really hard to make sense of this, and it's hard to kind of read this, and nobody does it like this. People are just looking at computer-aided design tools, and you're seeing stuff. Your CAD tool, if you look at it, what does it look like? It looks like this. If you were going to draw this in your CAD tool, it would look like this. Of course, it wouldn't be blurry. So, and each one of these layers would have like a different color so you can see what's going on. You know, poly will be in red, active will be in green, or whatever you selected. And then you can go through in your CAD tool and select the different layers separately. So you can make sure, like, you select here and go, is there a contact there? Yep, and I'll tell you, yes, there is. And you have these design rule checkers that tell you if you violated any of these things. Okay, so actually let me talk about that. So just as there are computer-aided design tools that where am I? What was that? Yeah. So we talked about there's computer-aided design tools that go from Verilog to a synthesized net list to a place and route. So, okay, let me take a step back. So if this is a field, chip design, where the computer-aided design tools are a huge part of the work. These are expensive tools. I hate to say this, but Cal Poly has access to millions and millions of dollars worth of these tools. If you were a company and wanted to get the number of licenses that Cal Poly has, with I don't know how many millions of dollars it would cost you. But unfortunately, for various reasons, we don't have access to them remotely. Anyway, but the computer-aided design tools are a huge part of the design flow. You absolutely cannot live without these design tools. So some of the design tools, like I mentioned, they are taking you from Verilog to synthesize netlist to place and route. Another set of important, so those blocks are now guaranteed to work from a certain standpoint. When you go from a Verilog netlist to a synthesized netlist, you're guaranteed that you're not going to get, if you were smart enough and used the right discipline, the right procedures to write your Verilog code, you're not going to get, circuits here that are shorted or otherwise, or have the wrong functionality. And same if you're going from here to here, you're not going to get circuits that, your synthesized netlist had a NAND gate, and your place and route tool is not going to go drop in a NOR gate or some kind of a shorted circuit or something here. So this is guaranteed by the computer-aided design tool, because that computer-aided design tool is a very sophisticated piece of software, and the manufacturer, the foundry, has spent a lot of time programming their design rules and their logic gates and all that into this tool. What you're not guaranteed to happen, though, with this whole flow, is that you're not guaranteed to get like a very fast speed necessarily. They'll tell you what speed it's going to estimate you're going to get, but if you want to, it's not going to be at the very highest speed, say, or the lowest power consumption. So if you want to do those things, again, you have to do this stuff, build these things sort of by hand. Now, you still have a challenge, though, because even if this is, 1% of the chip, the stuff you do by hand, and that's anything you do by hand is called a custom flow. This is called a place and route flow. I mean, there's different names for it, but the flow means the flow of your design flow. Okay, the design flow for a custom flow means you hand simulated that block, you hand laid it out, you connected the transistors by hand. Okay, so two very important things that come into this custom flow, because again, as soon as you get more than honestly, if you get more than 2 transistors here with all these design rules, so again, there's 50 masks. Imagine how many you have for each mask. You have rules for the sizes of what's in the mask. And you have rules for the overlap of those masks with other masks. I'm going to put up an example set of design rules. And usually they run into like hundreds of pages. Okay, so if you were gonna, like, all you had was a piece of paper and you were trying to like do this yourself, you'd really fail. So, but there's 2 important pieces of software. One of them is called the DRC software. Again, these are computer design tools for the custom flow. That stands for Design Rule Checker. So after you're done doing this, creating these masks, this process is called a layout. So drawing these masks is called a layout. After you've done that, you can run your design rule check on software on your drawing. Okay, you can run it on this thing that you've drawn in the CAD tool. And it's going through, it's already been fed all the design rules of the Foundry. Those 300 pages are in there. And I'll check to see if you have errors. You've drawn lines that are too narrow or too close to each other, or things that are overlapped. So this is an absolutely critical part of the process, okay, this DRC checker. The second thing you have is called LVS, which is layout versus schematic checker, schematic. Okay, so, and that basically, let's say you've, as you'll see in slide deck 4, let's say an inverter schematic looks like this in CMOS. This is VDD, this is ground, this is a PMOS, it's an NMOS, in, out, okay, which kind of coincidentally looks like this, because this is an NMOS, this is a PMOS. We don't see all the connectivity, but you could probably guess that it might be part of an inverter, let's say. So this layout versus schematic checker compares your schematic. So, you know, you draw the schematic, you run SPICE on it, etc. Kind of looks like, you know, you typically don't use something as simple as PSpice, use other pieces of software, but it kind of looks like what you would draw there. And it compares it to your layout. Because again, even if you're doing a custom flow, typically you're dealing with like hundreds, if not thousands of transistors. And if you try to connect things up by hand without having something to automatically check it, it's just not going to work. Okay, so a lot of this stuff is relying on these computer-aided design tools to make sure you get this process right, whether you're using a place and route flow or you're using a custom flow. So for example, if in your schematic, you were showing that you had an assumption that this metal line was connected to this metal 3 line. And by that would mean that, let's say, this metal 2 line in your schematic goes to an inverter input, and this metal 3 line is going to go to another inverter, and in your schematic you show them as being shorted. So they have the same input, and you didn't put a via here accidentally, you didn't draw it in. This would flag, your LVS would flag that in your layout, these 2 lines are not connected, that these 2 lines are not connected, but in your schematic, they are connected. So these are like sort of ways to double check what's connected and what's not. Okay, so some points, again, this is like, I'm really sorry, guys, this is like so difficult for you guys to use your imagination and for me to describe it. But contacts, okay, so Contacts are one of the key, both contacts and vias are key places where things go wrong as part of the manufacturing steps. Okay, the reason why is that they are usually very small, so that their dimension is small, physical dimension and that are drawn. And they are cutting through, usually it's cutting through a thick dielectric. So you end up with situations where your contacts are narrower than you think, meaning that you might end up with a high resistance contact. So you might end up with problems. So high resistance. Or worse, infinite resistance, meaning there's an open circuit where you thought there was a contact. And you got to imagine, like, you're drawing, you know, if you have 20 billion transistors on your chip, you're probably drawing like, you know, 100 billion contacts. And even if statistically speaking, you know, you have a very, very high percentage of good contacts, even a really low percentage of bad ones, and I'm talking about a really low percentage, could mean that you have an open contact somewhere, which means that your chip would fail because of that one open contact. So one of the main design rules, that it's actually not a design rule, this is part of the why it's mentioned here, but it's a very good practice. So I'll put this very good design practice, is when you can, is to put multiple contacts in parallel. Let's say you had a piece of metal, and we'll draw that in blue, a piece of metal 1 that you wanted to contact with a piece of poly. So here in this case, whoops. So if I draw this in a cross-sectional way, the poly is like sitting like this. The metal 1 is sitting like that. Okay, so I could either draw it like this and drop one contact in between these two. Okay, or if I can at all afford to do this, I could draw this out a little bit more and drop 2 contacts between these two. So basically what these 2 contacts are doing, the second contact is just shorting 2 lines that are already shorted. But if my first contact goes bad for some reason, again, statistically speaking, it's very unlikely, but even that small chance, when you're talking about repeated hundreds of billions, tens of billions of times, might happen at some point. So the first thing is you're dabbling up. If one of them fails, the other one will work. And the second thing is these contacts, for the same reason that they tend to fail sometimes, more than the other layers. For the same reason, they tend to have high resistance. So they're very narrow, again, very small, and they're going through a relatively thick dielectric. So it means they have a pretty sort of a small, narrow, pretty high aspect ratio. This is like a poor drawing. If I was going to draw, if you're going to see a really, I mean, this is not a poor drawing. It's a cartoon, right? If you were going to see a real contact, it would kind of like look like that. It'd be very, very tall and narrow. So it means that it has high resistance, relatively speaking. So again, if I drop 2 of them, the resistance of 2 is going to be half the resistance of just one of them, which means this connection will have lower resistance. It's not unusual for the resistance, especially in short lines, the resistance of the total connection to be dominated by the resistance of just the contact. For example, the resistance of metals are typically for typical widths or in the milliohms per micron of resistance, whereas the resistance of a single contact might be like 20 ohms or something like that. So you want to, so anyway, this is like really good practice to drop in multiple contacts where you can. Same thing is true for vias. If you can drop in multiple vias, okay, again, this is really, you got to do that if you can get away with it. Okay, so overall, let's see. So this is what, like, for example, an inverter looks like. So I said you would you'd start with a schematic. So this is like, I guess, looks to me like might be a PSpice schematic or something like that. It looks like a CMOS inverter. We'll talk about that in slide deck 4. And then this is what you'll end up with in as a layout. And this is an intermediate step to say what happens as you complete the layout. This intermediate step only has the transistors and the polysilicon. This includes the metal layers. So if you look at this, this is a poly that's going across a P+ layer. So this is a PMOS transistor. Okay, so, and the length of the transistor is this. The width of the transistor is this. So if I want to make this a wider transistor, as you'll see in, I think I talked about that in slide deck 5, the video from this. If you make this a wider transistor, you can have more drive strength, more current output out of this transistor. So you would draw it basically wider. You would extend this P+ and extend the poly out here. And this is an NMOS transistor because I got, a poly overlap to this active. And again, this is the length and this is the width. Okay. Now, because it's a very short segment, I could just short these two polys together. So notice my input is a short between the gates of the P and the N. So sometimes you see this where people just use the polysilicon there to connect the two. And then these are the substrate contact for the NMOS, and this is the well contact for the PMOS. So this guy is this connection here. This guy is this connection here. Okay, this drain is this drain here. This drain is this drain here. This source is this source here. This source is the source here, and we'll talk about that more about source drain and what we mean by all that stuff. So that's what the transistor looks like. And then once you want to make the connectivity to this, you go to metal lines. And so you have a metal 1 here. There's a contact between metal 1 and poly. So these are these black boxes. And then I have an output, also has basically metal 1. So that's a metal, I would have drawn a metal 1 like this here. And then contacts to have them connect to both of these drains. And then I have another metal 1 that goes to VDD, and a metal 1 that goes to ground. So those are what sort of going from schematic to layout looks like, and just the transistors look like that. So again, this talks about the design rules. The design rules include minimum size, like, hey, don't make anything narrower than this size. Don't make anything too close to each other. Make sure that, there's a minimum overlap of one layer to another one, just so the manufacturer can fabricate this. Okay. I'm not going to get into these Lambda-based design rules because it's like overly complicated. And again, we won't be able to really mess with this stuff without, it doesn't start almost not making much sense to get into the gory details without having the computer-aided design tools. So I'm not going to go into these. And you're going into the industry, you're not going to really run into Lambda-based design rules. It was really something that was created for universities. Long story and had good reasons, but anyway, it's not going to make much sense to talk about. Okay, but here's something that's kind of important is that, and this will come up, is that there are, there is, when you look at the CMOS logic family, as we'll look at in the next set of slides, you have really two concerns. One of them is current, and the other one is capacitance. So current and capacitance. Together, they decide how fast you can go. Okay, the reason for that is, if you look at sort of a very basic equation for charge and voltage. So let's start with Q. Charge is capacitance times voltage. So somehow we want to get current out of this. Well, current is the change in charge for a given amount of time. So dq dt is c dv dt. I'm just taking the derivative of both sides. So dq dt is just equal to current. Okay, that's the definition of current. So if I want to look at dv dt, I'll get I over C. So why that? Well, think of a rise time of a logic circuit. Somehow the logic circuit, let's say it's going from a 0 to a 1 state, that has a certain finite, in reality, it'll have a certain finite amount of time that it takes to take that step. Okay, let's say, since in a real world, a logical 0 will be actually 0 volts, and a logical 1 will actually be, say, 1.8 volts for sake of discussion. Okay, so you're taking this 1.8 volt transition, and you want to do that as fast as possible in your logic gate. You want it to be kind of a, ideally, if it didn't cost you anything, you want that to be an infinitely fast step. So if you guys are doing like Verilog simulations, etc., I don't know if you guys are familiar, if you guys already worked with Verilog or not. These just look like sort of straight, this is what logic pulses look like. They just look like they have an infinitely fast rise, infinitely fast fall time. So that the amount of time it takes to go from 0 to 1.8 is the dV will be 1.8, and the dt will be the amount of time it took you to get there. So with this equation, you'll see that the higher the current, the faster that transition is going to be. And the higher the capacitance, the slower the transition. So basically, when it comes to speed, if you have high-speed circuits, you want to maximize the current output and minimize the capacitance of your circuit. So that's the first thing you'd like to do in terms of performance. So if you guys remember, the quality of your design, you defined it as having certain parameters. One of them was the speed. So quality of design. 2 was the cost. I usually translate to the area of the circuit. Speeds translating to capacitance and current. And then there's power consumption and reliability. These are some of the important things. So right now, I'm just talking about speed and cost, okay? So one thing is, speed is you want to basically minimize the capacitance, maximize your current. And cost, you just want to plain old make things as small as possible, your transistors as small as possible. So usually you can't, these are like trade-offs you need to make. There's one place, there's a couple of tricks you can do to sort of get these things for free, essentially, okay? And I'm just going into this because this is something that we'll end up seeing later in our schematics and SPICE simulations and so on. The first concept is the concept of transistors in series. Okay, if you have 2 transistors, unless we draw each, these are 2 NMOS or 2 PMOS transistors. Okay, so we drew our NMOS transistor like that. And this is the gate of 1. So if I put another one next to this one, so if I had this gate A, get this gate B, okay, it would look like this, okay, if I drew them. But if they're connected such that, let's say they're actually in my schematic, they're connected, whoops, in my schematic, they're connected like this, meaning that I have an input here, these 2 are connected, and the output's over there. So I have an input here, these points are connected, and the output's there. I can basically, there's no reason for me not to merge these 2 nodes. Okay, so I don't need to put a contact here and contact here. I could just have them share the same node here. So this is going to be n plus because of this connectivity. The 2 similar transistors, same type of transistors in series without a connection needed in your schematic to this point, then I can just put these guys really close to each other because I don't need to put in a contact here. The contact takes space, and then there's a separation from the contact to the polys. So basically, I can merge, basically get rid of the contact and have these so-called finger transistors. So this way, I've saved this space. And so my cross-section is going to look like this. So instead of that, I'm going to have again, I can get this because this node is shared by this. So it's basically I've saved a bunch of space here, and I get that for free. So whenever you see a structure like this, it's always laid out like this as opposed to 2 separate transistors connected with metal lines together. Okay. So that's to save space. And when you have transistors in parallel, it's somewhat a similar idea, but it's a little bit more complicated. So there, again, you can share a node. Okay, in this case, this is shared. So I didn't have 2 separate N plus layers, 2 separate N1 boxes, N plus boxes. I just have one N plus box. But it's not as efficient, it's not as tight as this layout, because I need, notice I am making contact to both ends here. So I need to connect these 2 points. So it'd be like this point. And I need to get a contact to this middle point here. So it's not as tight as this, but it's still tighter than if I made it 2 separate transistors. Now, another advantage that this gives me, so how do you, well, another advantage is that even although I've made the contact to this point, notice that there's less diffusion here. Each, as we'll see in the slide deck 5, each diffusion area has a capacitance associated with it. So if I can reduce the area of this diffusion, I'm also reducing the capacitance. So if this is my output node, I have reduced the capacitance of this output node. If this guy still hasn't reduced the capacitance, but let's say this guy goes to ground, you'll see this would be like a, in the case of an NMOS, this will be a NOR structure. Then this point would be connected to ground, and I don't care about the capacitance. So we'll see that. But it ends up that basically you can get area, so it means cost, bring some of the cost and improve some of your performance basically for free if you use these kind of finger approach to your layouts. And again, the reason I'm mentioning this, because we won't be doing layout, is because we'll be using these concepts in our sort of circuit parameter studies. Okay. Okay, so I'm gonna, let's see. I'm gonna stop slide deck 3 here and move on to slide deck 4. Okay, so now, okay, so that was how you build and lay out the CMOS gate, or in a CMOS process. So let me just start you guys off, and I will go, I'm only going to get a few minutes here. So I'll go over this again in your, in the next lecture. But let's say we want to have a CMOS gate. What does that look like? So remember, what we're trying to do here is we're trying to be able to make structures that do binary math. And those are logic gates, things that can do that. So for example, we need, inverters. So an example of an inverter is, the input is 0, the output is a 1, and then when the input is a 1, the output is a 0. Okay, for example. Or, another thing that's really ends up being really a popular logic circuit is a NAND gate. That transfer function, I always have to write it to remember it. Maybe out. So 0, 0, 0, 1, 1, 0, 1, 1. And the out looks like 0, 1, 1, 1, because it's a NAND. Okay. And so on and so forth. You have, 3 input NANDs, 4 input NANDs, you have NORs, and multiple input NORs and those kind of things. You have exclusive ORs, so what are they? Inverters, NANDs, NORs, XORs, and so on. So these are the logic elements, logic gates you need to do binary math. So we're going to use, we're in a CMOS process. So we're stuck with these basically the two tools we have are N MOSFETs and P MOSFETs to build these logic gates. Okay, and each one of these transistors is a pretty complicated beast. Assuming you guys have taken some microelectronic classes before and you're familiar with them, you'll know they have, these complex, it's a 3-terminal device, each one of them, gate, drain, source, and it's a complex current versus voltage relationship depending on what you do to those inputs. But in this lecture, we're going to start looking at how, basically making an assumption here, making an assumption that an NMOS with the gate being a logic 1, we can treat it as a closed switch, and a gate being logic 0 will act like an open switch. And a PMOS with a gate equal to 1 is an open switch. And a gate equal to 0, it's a closed switch. So with that assumption, which is, we'll start with that assumption in this slide deck 4, we're going to try to build a logic family that is optimized in different ways. Okay, optimized in terms of power consumption, area, speed, and so on. And also in terms of reliability, meaning that you can get the highest noise margin and, a good sort of quality signal, a good clean binary or logical signal from layer of logic to layer of logic. Okay, so we're going to see how, given these two types of devices, we can make different gates, and why does this topology for a gate known as the CMOS gate is why it's ended up where it is, why it's better than what came before. Okay, so anyway, we'll start digging into this on Thursday. Any questions on what we talked about today or previous lectures or anything? No? Okay, then I'll let you guys go. I'll see you guys on Thursday. Take care.
Thank you, Professor.
Thanks. Bye.